The snout with the bioskirt is for hydrocarbons. Hydrocarbon targets are fueling facilities and convenience stores, fast food outlets, beach or waterfront discharges, marinas, ports, transportation facilities, vehicle service or maintenance facilities, solid waste transfer stations. These are all things that have a lot of hydrocarbons, and the bioskirt is a real good add-on to a water quality hood that will help you keep the hydrocarbons in the structure under a high flow event. Even though there may be some hydrocarbons on the surface, the turbulence in the structure can emulsify those hydrocarbon particles and flush them downstream. Here, the bioskirt locks them into the structure and allows you to keep the hydrocarbons in the structure even in a high flow situation. So it's a really good add-on for those applications. The bioskirt specification. Key points. The bioskirt is always used with the snout hood. Bioskirts come in one size, so you'll use multiple bioskirts for larger snouts per the deployment schedule. The bioskirt is effective for emulsified oils and PAHs. The next accessory we have is the stainless trash screen. And it's important to have a trash screen design that does not completely block the pipe. There's a lot of plastic and other devices that basically butt up to the pipe outlet. And these are simply nothing more than pipe plugs. They become clogged, and 90% of the time they just get pulled out of the structure. Here, the trash screen goes into a sumped structure. So the water level rises in the structure, continually cleans the screen, and the screen is open on top, even though that opening is going to be above where the invert of the pipe is. So there's always going to be a water layer in the structure that prevents floatables from going downstream. This is essentially a no clog sort of trash screen. It is qualified as a full trash capture device for areas where that designation is important. The typical perforation is 5 millimeters or 1/4 of an inch, and it's used to cover the outlet pipe. And there are many sizes of trash screens available to cover the snouts. Now, when designing with the stainless trash screen, make sure that your structure wall where the outlet pipe exits is going to be wide enough, not just to accommodate the snout, but also the trash screen, which will be wider than the widest dimension of the snout. And all of the trash screen details are available for download on the website. So the newest structural item that BMP has developed is the turbo plate. And we wanted it to be a retrofittable item for a sump structure. We wanted it to be low cost to fit with BMP's design philosophy. And we wanted to be able to provide performance estimations through software that will help you calculate what sort of performance you could get by employing snouts and turbo plates. The other goal, of course, was to make it adaptable to both round and square structures and deployable in a variety of structures for increased performance. So that's what we've done with the turbo plate, and we'll take you through the development process and how to apply it. So the resources that we have for using the turbo plate are the specifications, the design schematics that lay out a structure and talk about the different turbo plates and snout sizes that we're going to use based on the inlet and outlet pipe sizes and the flow. And then we have CAD details for the 12 series, the whole way up to the 36 series turbo plates. So those are available for download on the website. So how do a hood and anti-turbulence plate work? Well, the water for use with an anti-turbulence plate will be directed through the inlet pipe. The inlet pipe will then have a solid plate in front of it that will redirect the flow to perforated plates. And these perforated plates, because they increase the surface area that the flow sees, will reduce the velocity and thus the turbulence. With lower turbulence inside the structure, the pollutants separate out and settle And that allows the pollutants to stay in the structure, even under higher flows, because the less turbulence will mean less scouring and resuspension. And then the cleaner flow will exit from the hood. So that's essentially how the turboplate system works, with the solid plate redirecting the flow to the perforated plates that then knock the velocity and turbulence out of that structure. BMP did more than 50 in-house tests when we were developing the turboplate. And it was essentially to provide proof of concept in the initial tests. And then we zeroed in on the combination of plates and snouts to maximize performance. We were able to get to almost a 75% removal rate with a snout, an inlet, and 2 side turbo plates. And with 2 structures in line, we were able to achieve over an 80% removal rate. And the simulated flows that we used in the house with Froude scale simulation was between 1 and 1.5 CFS. So it was a pretty aggressive flow regime. And we were able to get consistently good results in our test that proved our concept and brought us to the next step. So that next step was testing at Alden Labs in Holden, Massachusetts. They're one of the foremost hydraulic labs in the world. And we did a number of tests there in full-size snouts, full-size turbo plates, full-size structures to actually get data that we could then use to project performance for other applications in the future and to verify our concept. We tested a snout alone for a baseline, and we saw 64% removals with that. And when we added 3 turbo plates and a snout, we increased that removal to 80%. Now, it's important to understand that the removals with the snout and with the snout alone was your bigger particles. And then when we added the turbo plates, the finer particles were also being removed. These particles are much harder to take out. So that increase in performance was completely with smaller particles, which is a very important part of the benefit you get by adding turbo plates to your sump stormwater structure. As you can see, the variety of flows were shown, and for the test flow, which was 225 gallons per minute, the snout showed an 80% removal rate with the 3 turbo plates. The snout alone showed a 64% removal rate, and a full report from Alden Labs is available upon request. So how do you design with anti-turbulence plates? Well, you need your typical catchment data, the area of the catchment, your average slope, hydraulic length, curve number, and those sort of things. And then we can, once we have that watershed or catchment data, we need to get a pipe size, a treatment flow, and then we're probably going to recommend the size of structures, but you can let us know what size you would start with, and then we can analyze that and then determine the hood, the plate, and the structure sizes that will best meet your performance requirements. And I'm going to talk a little bit in an upcoming frame about the software that we have that helps us quantify performance. But what's always going to happen is your inlet plate is going to be solid. So that would be plate 1. And then that would direct the flow to plate 2, which is perforated. And then plate 3 will also have a benefit of just reducing any swirl in the structure and knocking down scour and potential resuspension. So that is your best scenario for the highest removals in a structure. The hood and plates will work for both round structures and rectangular structures. And if you can have a structure with a snout upstream of the turbo plate structure, your performance will increase as well. So the turbo plate performance prediction software is a great addition that we brought out this year. after we had accumulated a substantial amount of data that we could put into the model that helps us make predictions. So what we need to make the predictions are the flow rate, the structure size, the sump depth, and the BMP components. So basically, the engineer needs to let us know what sort of criteria or what sort of performance you're looking for. And then we can look at the flow rate and then make structure size, sump depth recommendations and the BMP component recommendations. And we can try to tailor a structure to a given requirement. And again, all of the performance predictions that we make are based on our test particle size distribution, which was 50 to 1,000 micron particle size distribution.